Hello guys, this is Abhay Sharma for thinkingpenguin.com and welcome to another tutorial. First of all, sorry for the delay. I was really busy in a freelance project and now it's finished and I am back. So in this tutorial we are going to talk about loops in animation node. Yes, finally. It's really the holy grail of animation nodes. It's difficult, but once you understand that, it feels like you got some kind of superpower. I have so many ideas about doing some really exciting tutorials, but I can't make it unless I explain the basics of animation nodes. And this is a big step. So let's get started. Loops are basically used for doing repetitive tasks. It can be of two types. In one kind, you know how many times a loop has to run, and in second, you don't know how many times a loop has to run in order to finish the task. It sounds very technical and boring, but if you really pay attention and look outside the box, you will see loops are everywhere. There are so many loops already running. When you turn on your machine, a program called BIOS starts to run, and it's running in a loop, and it will keep running unless you exit the loop. Then there is your operating system running in a loop. Then there is Blender running in a loop. Then there is animation nodes running in a loop. So it's like loops running inside a loop to basically create a system. And this concept really extends beyond computers and programming. Time is a loop. Life is a loop. A human body running lots of loops. Your heartbeat, your breathing, your brain, your visual cortex is processing 24 frames per second to construct the reality. Remember, in conditions tutorial I said that conditions makes your program smart. Well, loops give your program life. Okay, let's jump into animation nodes. When you create the first node in animation node and if everything is at default settings, you will see there is a counter starts running here, which is basically tells you how much time a loop took to run a single iteration, and it keeps running unless you change the settings. I'll go slow and simple as far as the example is concerned so that we can focus on loops. So let's create a Suzanne object first, scale it down and apply the scale. I'm gonna change this panel to outliner and let's hide Suzanne for now. Let's switch into edit mode, and what we're gonna do is we're gonna place our Suzanne on each vertex of this cube, and we'll do this without using loops so that we can understand how much manual labor goes into that. So create a mesh data node. We'll select our cube. We have 8 vectors corresponding to each vertex position in 3D space. Now we will create a transform output node to position the Suzanne on these vertices. Select our Suzanne. Now let's turn on the visibility and location controls. And now we can connect vertex location directly to the location, and animation node will automatically insert necessary nodes to make it work, or we can simply create a get elements node by ourselves. Connect vertex locations to list and element to location. You'll see our Suzanne has jumped to the first vertex of the cube because currently the index is set to 0. If I change the index, you can see our Suzanne jumps to that corresponding vertex. Let's disconnect and move it away. Now what I want is to place copies of Suzanne on each vertex of the cube. So we need an instancer node. Select the Suzanne and hide the real object. Now I'm going to create 8 copies of Suzanne. Let's duplicate the same get element node and connect it with the instancer node. Now we can connect object to object and element to location. Now we can see a Suzanne object popped on the 8th vertex because right now the index of both get elements node is set to 7. Let's set them to index 0. So basically first object in the object list is positioned at the first vertex in the vector list. Change the index to 1 and 2 and you can see what's happening. I can also create an integer node and connect it to the both index inputs and can control both of them with a single input because index is an integer data type. Let's change the value from 0 to 7 and it will position all the Suzanne objects on each vertex of the cube. But the problem is once you move the cube, you can see all the Suzanne objects left behind, except the last one. That is slightly weird, but that's not a big deal. Let's do the same process again. This is called iteration. I'm going through each object and each vector in the corresponding list at that particular index. We move the object again and we have to iterate again. You need something here to keep this index running. This is manual labor and it's very simple right now. We are only dealing with 8 objects. You can imagine what will happen if things get complicated. That's when loop comes into the picture. Let's create a loop node from subprogram menu, or you can also create it from here. It's very interesting why it's in subprogram category because loops are separate programs. They have their own objects. We'll talk about that later. There are actually two parts of loop in animation nodes. First is this inside node where you do all the data manipulation stuff, and second is this invoke subprogram node, the outside of loop node, which handles the data communication. Basically, what comes in and what goes out is being handled by this node. It's like the train man from Matrix movie, if you remember. Let's see how many nodes are really associated with a single loop. So beside these two nodes, there are generators which let you output the data from the loop via invoke subprogram, and then there is this break condition node buried deep into the settings. It is very underutilized tool, but in my opinion it's really powerful and it saves a lot of time. It's a boolean type node which lets you control when the loop should run. It's same as if you go to the settings and you can see bunch of boolean controls to control the execution of master loop of animation nodes. So if you see closely, what's the common factor between these four nodes? It's their color, which defines that they are part of a single loop network. We'll talk about that later on. Let's delete these nodes for now and focus on the main task at hand. But first let me show you how loop looks like in programming. That's a simple for loop, iterating for 10 times. I don't want to talk about here, but frankly, that's a very simple thing to understand in coding. But implementing the same concept in node based workflow is kind of complicated. Only a genius like Jax Luke can do that. I have worked in many node based systems, but never seen this kind of implementation. Normally, they hide it, probably to avoid confusion or sheer complexity. Okay, let's do that what we were doing. So I'm going to bring this transform control here. Let's move these nodes closer. I'm going to move these get element nodes here. So how do we do the same thing? Positioning Suzanne on each vertex of the cube with loop node. First we have to import that data into the loop. For that we have to create proper variables or data types. It has to come through trainman, the invoke subprogram, but it has to be created in the loop node here. I'm going to import the data as parameter. So there are two ways you can import data in a loop, as a parameter or as an iterator. With parameter, you can create single value data types like an integer and list data types. But with iterators, you can only create list data types. We'll talk about iterators just in a second. Parameter type data import won't do any manipulation while carrying the data between invoke subprogram to loop node. It will come as is, untouched. So let's create a vector list parameter to import vector positions. And an object list to import copies of Suzanne. Now you can see it has been imported as a list. So let's connect list to their respective list inputs. Object to object and element to location. Now for controlling the index, we have used an integer value for the previous setup. Here in loop, iteration input in subprogram node and index output in the loop node will take care of that. What we have to do is just specify how many times the loop has to run. That's all. I'm gonna set this to 8. This iteration parameter input corresponds to this iteration output in the loop output node. If I see the output of the index, it displays 7. Don't confuse it with static data. It's actually changing in every iteration of animation node's main loop. It's changing very fast so that we can see the last number. Let's connect the index to index. Let's set this to 0 and move the cube. Now let's change the iteration value. Okay, so far so good. Look exactly same as before, right? But when you move the cube, you will see all the Suzanne objects are moving with it. That's loop. It's doing all the manual labor for us. Alright, so right now we have imported the data as parameters and we are using getElements node to retrieve elements from the list based on that index. There is another way which is more suited for these kind of operations. That is import the data as iterator. And that will simplify the loop as well because then you do not need getElements node. Loop node will automatically do this for us. So let's disconnect these nodes and delete these parameters. Now we will create two iterators, object list and vector list. Connect these inputs and notice the kind of output we get in the loop input node. What we have inserted in invoke subprogram node is a list, but we are getting here is a single element because the loop node is doing this get element per index thing internally. So now we can delete that. Let's connect it with the transform node and we have got the same thing. Notice that the iterator parameter from invoke subprogram has gone. Then how does it know how many times a loop has to iterate? Well, it knows because it has calculated the list length internally. You can see the output of the vertex locations. You can see the list length is 8. Or you can also create a list length node to check that. So this loop is iterating through each element and positioning each copy of Suzanne on each vertex of the cube. So this is how you import the data in loop. What about exporting the data? Well, it depends if it's a single value data or a list of data. If it's a single value data, you can directly connect it and use it. But if it's a list, you have to use generators. So create a generator. You can see there is a output slot added to the invoke subprogram. Let's add a mesh object node. I want to export the vertex location of each Suzanne object to a single vector list. So connect the object to object. If I see the output of the vertex location, you can see each Suzanne has 507 vertices. Let's output that. But here is a slight problem. The output of the vertex location is a list and input of the generator is not a list. And also we have to deal with the index. Let's connect the index to index and see what happens. It only outputs 8 vector locations because the loop is running for 8 times. And also these vertex locations are not from a single Suzanne object but from all Suzanne objects at specific indices. To fix this, you can change the mode of the generator node. Let's change the mode from append to extend. And now you do not need these nodes because the input type of generator node is now a list. Now we get all the vertex locations. Alright, let's do something with this data. Which also brings us to the point where we can see how parallel loop works. Parallel loops are like loops running with the other loop in parallel, but one loop is dependent on the output of the other loop. I'm going to create a cube object, scale it down, and apply the scale. I'll scale up the Suzanne a little bit. Now I'll position the copies of this cube object on each vertex location that we got from invoke subprogram. Let's create a loop node. Notice it has a different color. Let's create an vector list iterator. Create our invoke subprogram node. Connect vector list to vector list. Now we need an instancer node. Select our cube or just eyedrop it. For instance number, we know it's some 4000 objects. So either we can enter it manually or we can just simply connect it with the vector location list. It will automatically insert a list length node. You can see performance has degraded a lot and we haven't used these objects yet. Let's create an object list iterator. I'm going to disconnect it for now because it's really slow. Let's create a transform node and connect it. Now let's activate the instancer. My god, that is so slow. Let me turn off relationship lines, see if it helps. Nope. So now what? This is a real world problem. I have seen many people doing the same mistake over and over again. Loops are processor intensive tasks, so make sure you are using loops when it's necessary. And chances are you are using loops when it's not necessary. You need to narrow down the use case. For example, maybe you can restrict it based on the visibility of the object or visibility of the layer, or if that particular object is visible in the active camera, or maybe in a specific timeline range, or you can combine all the conditions. The point is to make sure it's running when it needs to. Animation nodes does provide a way to control that, and that is called break condition. Let's select our main loop. Let's rename it. Alright, if you select the main loop node and go to the settings panel, you will find a button called new break condition. Click on it. Right now it's active because it's checked. Notice this time counter at the upper left corner. Right now it's 40 to 50 milliseconds. If I uncheck that, it falls below 1 millisecond. You can imagine how much time it can save for you. So what I'm going to do is I'll restrict the loop in a certain timeline range. I'll create a time info node and then I will compare it with my values. Let's say between 10 to 20. Let's combine it with logic node. Connect it to the loop break. Now my loop will only run between frame 10 to 20 in timeline. that is 11 to 19 frames. Let's animate the cube. Play the animation. You can see it only activates when my timeline header reaches frame 11. This is just an example. Okay, let's move on. There are a couple of things I want to talk about. Let me delete the second loop. Select the main loop node and go to the settings panel and open the color panel, and here you will see two color controls. First one is just limited to controlling the color of the selected node itself. The second control, network color, controls the color of the entire network. Very useful to identify which nodes are part of the single loop network. Okay, now let's create an integer node. I'm going to connect it to this loop network. So first let's connect it with invoke subprogram. And you can see it doesn't change its color. Why? Because it's outside the loop. Let's try to connect it with something internal like this index out. Now it changes the color. And now it has become an internal object of this loop. See that once again. Now let's see how two subprograms can share their internal data and what are the restrictions. Let's create another loop. Now I want to use this integer data, which is an internal data of the first loop, to the second loop. So to use this, we can create an parameter input here, an integer. Now I can directly connect it to the invoke subprogram of the second loop. Notice we didn't go through the first loop invoke subprogram. Now we can access the data. Let me create a math node just for an example. Now let's try to connect the math node input directly to the integer output without going through invoke subprogram. The animation node network stops. We can't do that. You have to go through invoke subprogram. So we can use single value data. What about a list? Let's create an integer list parameter and connect it. You can connect it, but as you can see, you will get access to only the first element of the list. If you want a list output, you need to use a generator node, and we have to use invoke subprogram to connect the data. So that's all for this tutorial, but we are not finished yet. There is one more very important concept left out, and that is nested loops, which is basically loops running inside each other. But not in this video because it's already gone too long. We will talk about that in the next tutorial, and we will create a 3D grid with that for an example. Now, you already know the basics of loop. I want you to try to make a 3D grid with whatever you have learned. So, let me give you a hint. This 3D grid has created here with scripts. You can see the for loop is running inside the for loop. Basically, that's what you have to create, a 3D grid. There is another way also in animation nodes. You can look for the reference. Let me give you the initial start. For visualization, you can use mesh object output node. Now what you have to do is repeat this row in y direction and then the entire 2D grid in z direction. So that's it for this tutorial. Give it a thumbs up if you liked the video, comment or share, and do subscribe if you haven't yet, and make sure you have clicked on the bell icon to get the notification whenever I upload a new video. Thank you so much for watching, and I'll see you in the next video.